And we're inputting on the base. We're outputting on the collector, so this is a common emitter amplifier. Voltage divider bias. And what we're going to do is we're not going to bypass it yet. I think we're going to hook this up later. What this does, it wants us to put, as soon as I focus back in, it wants us to put 1 volt peak to peak in, and then this voltage divider, if we calculated it out, that would put 10 millivolts right there. Well, the problem is our function generator will not put out 1 volt. It puts out about 2 volts, but I said about 2 volts. So what we're saying is it was extremely hard for us to try to get 10 millivolts out when all function generators put out those different voltages. So what we did is we took out this circuit right here and we replaced it with a potentiometer. So what can I do with a potentiometer? I can set any voltage I want, right? Understand that. So now this guy here don't really make that much difference. We'll put enough voltage in to make sure we get 10 millivolts. So what we're going to do is we're going to make 10 millivolts in, and then we're going to figure out what gain we're going to get. So before we bypass, we should get a gain of about 3. Okay. And then we'll bypass it, and we'll see the gain just goes out the door. So let's calculate it. What would dB be? What's our calculated dB? So here we are right here. So right here, this is what we're calculating right here. So over here on table 34-2, first thing we're going to do is calculate dB. Then we're going to calculate dE. We're going to calculate IE. Then we're going to calculate DC and DCE. Of course, all we're going to do is IE. We're not going to measure IE because we can measure pretty easy. So this is right off our worksheets, guys. And what we're going to do is we're going to calculate it, and then we're going to measure it and see how close we are. And this is a real life circuit, right? We got it hooked up here. Here it is right here. So here's my transistor right here. It's a 2N3904, which has a typical beta of around 100. And it's pretty close to 100, even though if you look at your data sheet, it says 30 up to 300. In this circuit, it has a beta of about almost 100. Here's my input capacitor. Here's my output capacitor. Here's my 10K. Here's R2. Here's R1. Here's my collector resistor. Here's RC. And here's my emitter resistor. That's the 2.2K. This is a 5-band resistor, by the way. So a 5-band resistor goes number multiplier, and then tolerance. So what y'all doing for me is you're calculating these voltages. And what we're doing here is we're going to calculate them, and then we're going to come up and do what? So let's just write them on the schematics. What do y'all get for V? What do we got for VE? Or VB. And then y'all record them in y'all's table. And 1.75 volts. Is everybody okay there? Everybody okay there? Okay. And what are we going to have for VE? That should be pretty easy. We're just going to subtract 7/10 from it, right? If I can do that in my head, 1.05 volts. Yeah, 1.05. Then we're going to calculate IE. So we know RE, we know the voltage drop across RE, so we can calculate IE. So IE would be equal to 1.05 divided by 2.2K. What does that give me? What's that? 48 micro? Then we could calculate VRC. So VRC is going to be equal to 6.8K times 48 microamps. Now you have to understand it's going to be a little less than 48 microamps because remember, IE contains both emitter current. Okay. What's that? 470? 470? 477? Okay. Then we'll use 477. That's 22. I'm sorry. Y'all got the schematics of it. So VRC would be equal to 6.8K times 477 micro. So what would VRC be equal to? 3.10. 3.2 volts. Now I didn't do that in my head. I calculated it while ago. I just wanted to make it look like it was small. Then I can calculate VC. So VC is going to be equal to 10 minus 3.2 volts. So what's VC going to equal to? What's that? 6.8. So we're biased toward cutoff, right? Y'all understand why? Because we got 10 volts right there. We would want this right here to be 5 volts. Sorry. We'd want this right here to be 5 volts. If this was 5 volts, then that means it would be biased in the center. But we got it biased at 6.8, so we're biased toward cutoff. So when we start increasing our signal, we should see the top clip first. And so voltage collector to emitter would be the voltage on the collector, which is 6.8, minus the voltage on the emitter, which is 1.05. So what's my voltage collector to emitter? 5.75, 5.8 volts. So are we operating in cutoff, or are we operating in saturation, or are we operating in the active region? So this should be something that you should know. I mean, this is probably one of the most important measurements you have. Are we operating in cutoff? If it was operating in cutoff, this would equal 10 volts. Does it equal 10 volts? No. If we was operating saturation, it would be less than 1 volt. Is it less than 1 volt? No. So we're in the what? We're in the active region. Okay. So now we're going to measure these. So now y'all can fill in your chart over here. So you know what our computed VB is. You know what our computed VE is. You know what our computed IE is. And you know what our computed VC is. And you know what our computed voltage collector to emitter is. So now what are we going to do? We're going to measure. We're not going to measure IE, but you understand that if all these calculations come out right, then IE is pretty dang close, right? So here's my meter. So what I'm going to do is I'm going to take my meter, and which one do we need to measure first? VB. So here's my two resistors here that makes the base. So I'm just going to touch it right here on this guy right there, and it's supposed to be 1.75. And what is it? 1.7. Isn't that neat? Now why ain't it 1.75? Well, we're using approximations, right? You understand? We're thinking we're using the exact values of these resistors. Okay, what's the next one we need to measure? VE. So here's my base resistor. It's supposed to measure 1.05. It's measuring 1.04. Is that pretty neat? IE we're not going to measure. Here's DC. We calculated it was going to be 6 point what? 6.8. Here it is right here. 6.67 or 6.7. Not bad, right? But see, I know this amplifier is working great. I just don't have an input signal on it, but I know it's working great. Because I took my calculated values and my measured values are about the same. Now, voltage collector to emitter, we'll have to take off Here's voltage collector to emitter, so I got to take off my common. We don't like to do this. Normally, what we do is we would compute it just like we did before, because we don't like to put two probes into a circuit. But this wants us to measure it, so we will. So this is the voltage collector to emitter right here. It's measuring 5.7 volts. What did we calculate? Not bad, right? Pretty good. Now what we're going to do is we're going to come up here and we're going to bring our function generator out. What frequency do we want on our function generator? So here's my pod. It's hanging down here. I have one lead connected to ground, and then my function generator I'm going to hook up to this other lead up here. And then my center is going into the base. It's going to my base capacitor, which is this capacitor right here. So what are we looking for on this thing? We'll go ahead and set it up, and then we'll redo it. I'm going to hook up my scope to my function generator. What's the frequency do we want? 10K. What frequency does it say we need? 1K, 1 kilohertz. Okay, so we'll set it at 1 kilohertz. Wrong way to do it. That's close enough. And then I'm going to come over here. So this is my function generator. I got it set on 1043 hertz. It's good enough for these, right? Okay. And then what I'm going to do is I'm going to come over here and I'm going to disconnect my pot. I'm going to hook this up to that. And I'm going to adjust this down until I get 10 millivolts. Now we're going to have a little problem here. We're going to get as best as we can. So that's 100 millivolts per division. So we want it down on the best we can do on this scope is 2 millivolts per division. So we're going to try to get it down to 5 divisions. Looks like it's got DC outside. It looks like it's got DC on it. The problem we have is that when we get down to these 10 millivolt levels, it's really hard for the scope because it picks up so much noise. So let's see what we're getting on the base. Let's see what we're getting on our output. Okay. What gain should we expect? What gain should we expect? We don't have it bypassed. What gain should we expect? Anybody got any idea? So my gain is, what do I do about this one? I don't know. We'll look and see. That's a good guess. I mean, that sounds pretty good. What we're going to do is I'm going to come up here and I'm going to say R out would be equal to 1 over 6.8K plus 1 over 10K. So this is where our output is developed right here. So if you notice, we have two resistors, and we have those two resistors are in parallel, the load and the collector. So what would that be? What would my R out be? About 4K? 4K? This is what you learned in 4K? Huh? So, about 4K. And then my gain is going to be this resistor right here. It's going to be 4K divided by 2.2, so it's not a real good amplifier. So my AV would be 1.9, 1.8. Okay. So let's see if we can look at this on the oscilloscope. I need to get me a wire so I can stick it into this instead of trying to probe my scope probe. So here's my input. It's going to be hard to trigger on. The problem we have with this circuit let's see if we can drop it down a little more before it turns into an only. Now that's about the best we can do right there. So what we're putting in is we're putting in about 20 millivolts. 10 millivolts per division, 20 millivolts. And now what I'm going to do now is I'm going to move over to my output. Which is right here. So this is 10 millivolts in. This is my output. So it looks like it's about the same, but it's kind of misleading. So let's put a better signal in so we can get a better reading. This is what I want to show you. So I'm going to turn this down. And I'm going to start adjusting this up. So here's this. So you notice this is a real nice sine wave there. And I'm going to keep adjusting. We know it's biased toward cutoff, right? So I'm going to start increasing my input signal. You'll notice sooner or later, you can see what's happening. The tops are flipped off. Because what we're doing is the input signal is turning the transistor all the way off. And if it's turned all the way off, all you got to work with is 10 volts, right? You understand? We can't get 11 volts out of the thing because all we got to do is work with 10 volts. Now, eventually, you'll overdrive it on both directions. You'll see the bottom start clicking. But what we're going to do is we're going to get this so we can get our gain down pretty good. We'll get a nice sine wave. So here's my input. My input is 2 volts. I'm sorry. Yeah, 2 volts peak to peak right now. And then I'm going to go to my output. And that would be 1, 2, 3.5. So 3.5 volts out, 2 volts in. What's that gain? 3.5 divided by 2. Plus a gain of 1.16. We calculated it's going to be about what? 1.8. So that's really, really good. Okay, so let's see what we can do with the lab. So what does it say I'm going to put in? By the way, on this one, they're calling RE prime. They're calling it this little RE. So how do we calculate RE prime? I'm in table 34-3. And we're not going to be able to see 10 millivolts. So we'll just see what we can do here. So what's RE prime? So RE prime, how do we calculate RE prime? 25 millivolts over IE, good. So my IE that we calculated was 477. So I'm going to say 25 milli divided by 477 micro. So that's RE. Don't look like we're out of time to finish this. What's that? 42? 52. Okay. So that'll be RE, 52.4 ohms, right? AV, we've already calculated. Our computed AV is 1.8, right? VC, we calculated our VC was what? VC computed was 6.8. And then RN. So let's look at RN. So this is RN. So what I'm going to do is this is my circuit. And of course we haven't gone over this, so we have, but let's see how many of y'all remember this. So this is what my AC signal sees. And it sees this so this would be 47K. This would be K. This would be the 10K. So this would be R2. And then this is going to be 2.2K times beta. Now typical beta I said for this is what? 100, right? So this is Rn computed is going to be equal to 1 over 47K plus 1 over 10K plus 1 over 2.2K times beta. Let's go ahead and do that so we won't have to do the math over there. So what's 2.2K times 100? 22K, right? Right? So what we're going to do is, it's a parallel circuit, which is pretty neat. It's just that the only little thing that we got to understand is that this, from the signal point of view, this resistor right here is times beta. So what is our computed Rn going to be? And we're going to measure this too, by the way, next class. So, let's see, 47 times 10 to the third reciprocal plus 10 times 10 to the third reciprocal plus 22 reciprocal equals. So I got 6.9K. So what y'all got? And we'll see later on how we can measure it. It's really neat, the little trick that they came up with. 6.9K, y'all double check them on because I went through that pretty fast. Sounds about right. It's going to be less than 10. And greater than 22. I'm sorry. It's going to be less than 10. Because it's parallel, right? Is that right? 6.9K? Is that what y'all got? And by the way, I broke a cardinal rule. I didn't put any units up here. So what we'll try to do next class is we'll come up here. I'll leave the amplifier set up. And then we'll come in. So what have we done so far? We're not using any measured values, by the way, so y'all can just mark out this on your lap book. We're going to use calculated values. We're going to use color-coded values because we understand why our calculations are going to be off. We've already filled in this chart right here, table 34-2. We've already done that, right? Okay. So what y'all got to do is you got to, on this lab right here, what do you need to do on this during the weekend? You need to develop these characteristic curves, right? Everybody okay there? And then what else do y'all need to do? And you need to calculate IC over there on the left. You need to calculate IC on 33. To do your characteristic curves, some of y'all already did it. You said the maximum is 25. That's got to be done. You got to do your characteristic curve on 34. And what else do you need to do? You need to answer the question. Right? So this lab should be ready to turn in when they'll come back in Tuesday night. Keep up with your time, right? So you can fill out your time card over there. So that's the time you work on it at home too. And then when we come in on Tuesday, we'll knock this lab off. It shouldn't take us very long. And then I'll let y'all go to lab, and I'll hook up an AB amplifier for y'all and let y'all see how it works. And talk about what the reason of those diodes. And so, be in lab most of Tuesday night. We'll be in lab most of Thursday night. Not most of it. Thursday night we have what? We had it for Tuesday, but we moved it. We talked about it. We decided to move that Thursday. Y'all had a weekend before Friday. Yeah, I'll put that up this week. We finished it. We finished everything. So I'll put the test score review up there. Right. You can have all your checks. You can have all those copies complete. Y'all have been working on those. Looks like most of y'all done. That's it. Transit. Oh, it's fine. There's a couple of topics we'll discuss that. Remember, we have with all of them. You can take them twice. So the grades, those grades pop up on that. So you need to go back and look at it. There's one that's a little low. And it keeps your highest grade. So it's a win-win situation. So if you go back and retake it and you make a lower grade, you'll still end up with what you got, right? If you make a higher grade, it'll help you on that average. And those are about the okay, guys, have a good weekend. So look at that. We almost got 2 labs blocked out in one night. Which I wish I had all this math floating around in y'all's heads.